Hi students, today we will discuss the subtopic pipelining under the computer architecture, and the course of the computer architecture is UEC509. So now we will try to understand the data path in pipeline format for DLX processor. This is the data path for an unpiped line structure. As we have already seen in the previous slides, this is the data path for unpiped line. So as we will have to use the same data path for the 5 different stages, because as we will have to execute the a portion of the 5 different operations in parallel. So to reduce the complexity, we will not design or develop the data path with the similar circuitry. What will we do? We will write the short form of each and every stage. We will assign the each and every stage with its block representation. So the first stage, which is the instruction fetch, will be written with instruction memory, as the instruction memory is the most important part of this particular instruction fetch, because we'll have to fetch the instruction from the memory. So we will represent this particular stage of the data path as IM. Second stage will be represented with the register, as the registers are the most important part of this particular instruction decoder, because during the decoding the operands will have to identify, and whatsoever the data will be there in the operand will have to move to the temporary registers. So that is why the second stage, which is the instruction decoder, will be represented with the register. In third, the most important part is the ALU, because in the execution ALU is going to perform all the arithmetic and logical. Third stage of the data path will be represented with the ALU. Fourth will the data memory, as the data memory is the important part in the fourth stage. So and fifth again registers. So this is the data path of the DLX. So this is the DLX data path in pipeline format. As we can see that this particular portion is showing that data path similar to this by representing this data path with its block representation: IM for the first stage, for the first clock cycle, register for the second clock cycle, ALU for the third clock cycle, DM data memory for the fourth clock cycle, and again a register for the fifth clock cycle. So similarly, we can see that for the first instruction during the first clock cycle, IM means fetching will be there. During the second clock cycle, first instruction will move from the fetching to the decoding part, and it will be represented with the registers. And at the same time, during the second cycle, the second instruction will be fetched by the instruction fetch. So during the third cycle, the first instruction will move from decoding to execution unit, second will move from the fetching to decoding, and at the same time third will also be fetched by the fetching instruction fetch unit of the data path. And during the fourth clock cycle, the first instruction will move from the execution to the memory access, and from second will move from the decoding to execution, and third will move from the fetching to decoding, and fourth will be fetched by the fetching unit of the data path. And at the fifth clock cycle, each and every stage will perform whatsoever the operation is assigned to that particular stage independently will perform its operation. The fifth stage, which is the write back stage, will write to the register as per if the need of the instruction will be there. The second instruction will be perform its data access operation if required, and third instruction will be there in the execution stage, and fourth instruction will be there at decoding stage, and fifth instruction will be fetched by the fetching unit. At the fifth clock cycle, each and every stage of the data path will perform the independent operation. Okay, so this is the data path in the pipeline format. Now we will try to understand what are the different observations. What will happen if the things will be arranged in this way? Will all the things go smoothly? Will it be easy to perform each operation without any problem, without any hazard or without any obstacle? So we will try to understand this. We have observed the three different observations. Number one, the two separate memories, instruction memory and data memories, are required during the execution of one instruction. One, during the fetching, opcode will be fetched from the instruction memory. It is also a part of the memory. And second, during the execution, during the memory access stage, again processor will have to access the memory, which will be data memory during this particular stage. All those processors which are having only one type of memory under the von Neumann architecture, say along with the one set of address and data lines, in that particular cases or for such type of processors, this stage will not be possible, because at the fifth cycle the processor will have to access the data memory for its memory access cycle, and at the same time fetching unit will have to access the instruction memory. If a processor is having only one type memory, not a separate memory for data and instruction memory, that cannot be accessed. So that is why we require the two separate memories. One is instruction memory, another is data memory. Sometimes instruction memory is also called the program memory, sometimes it is also called the code memory as well. So to avoid the conflict of the resources between the instruction fetch and between the memory access, we require the two separate memory, instruction memory and data memory, under the Harvard architecture. Okay, so all those processors whose design is based on Harvard architecture will be having this facility, will have the two separate memories, or at least will have the two separate set of addresses and data buses through which the separate memories can be accessed. So this is the one observation. Second is, if we look at this particular structure, then we will find that in the second machine cycle, which is the decoding part, the registers will have to be used to identify or to load the operands for the execution of this instruction. And whenever we want to write back during the fifth stage of the pipeline, again processor will have to access the register. Now if we will look at that, so we will have to use the registers twice in a instruction. For unpipelined structure, there will be no problem, because all these two operations are going to be performed at different times. But in pipeline structure, because of the pipeline structure, these registers will have to be accessed by the two separate stages of the pipeline structure. One for the write back stage of the pipelining structure, and another is the decoding stage of the pipelining structure. So in this particular example, if we look at that, at the fifth machine cycle, the instruction 1 may require to access the registers of the processor, and at the same time decoding stage also required the registers. So now there will be a problem. How can we share or how can we assess the similar resource for two different cycles? So what will be the solution? Will there be any conflict in this particular stage? Yes, there will be conflict. And how can we remove that conflict? That conflict can be removed, as we can see that during the decoding stage, processor will have to read the operands from the register, so it can pass to the ALU stage. But during the fifth stage or during the write back stage, processor will have to write the data to the registers. This is the difference. Although for the both the stages, processor will have to access the registers, but in one case, in case of decoding, processor will have to read the data as operand to send it to the next stage for the execution, and for the write back, processor will have to write the whatsoever the data will be prepared by the ALU will have to write back to the register bank. So how can we avoid this conflict? This conflict can be avoided by dividing this particular cycle into two parts. In one portion, only written part will be activated, and another portion only writing portion will be activated. So in the half of the cycle, for the half of the cycle, the write back stage of the processor or the write back stage of the pipeline will write the data to the required register, and the second half of the cycle, the instruction decoding stage of the pipelining will assess the data of the register and will send to the data to the next stage. So by using this approach, we can avoid the conflict of the resources. By dividing this cycle into two halves, one will allow to write the data to the registers, and one will allow to read the data from the registers for the decoding stage. So by using or by doing so, we can avoid the conflict of the registers. The third is if we look at our data path, we have not shown the program counter anywhere because to reduce the complexity. In unpiped line structure, two program counters are written. One is this PC in the fetching stage, and second is this is also a performing the operation of the PC, is going to generate the address for the PC for the special instruction called branch. For the normal sequence of execution of the instructions, this particular PC will generate, or this particular portion will generate the new address for the PC, but during the execution of the branch related instructions, this particular portion will generate the address for the branch related instruction, because until the instruction will not be decoded, processor will not come to know that this particular instruction is belong to branch group, or this particular instruction want to jump or want to change the sequence of event. So until unless this instruction decoder will not decode it, after the decoding, then and then only the processor will come to know that what type of operation will have to be performed. So after the completion of the instruction decoder, processor will come to know that if branch instruction is required or not. If branch instruction is required, so naturally the new address will have to be generated, and then that particular address will be generated by this particular portion, and then it will be sent to the PC, and whatsoever the previous contents of the PC will be flushed out, and the new contents of the PC will be loaded, and accordingly the instruction will be fetched from the instruction memory. But same approach cannot be done in case of pipelining. Only one program counter can be used, and that program counter will be there in the instruction fetch cycle only. There will be no program counter in the memory access. So there will be no address generation will be there in the memory address. So the structure will be something like that. So for the pipeline, structure will have to be rearranged, and this structure will be something like that. So there will be no new address generation will be here in this particular stage. The address generation will be done in the instruction fetch stage of the data path. Although the detection of the branch related instruction will be done only after the completion of the decoding, it will not be assessed, but the address generation for the new instruction will not be generated here in this in memory access. So it will be done in this particular unit only. Okay, why we will do so? Although we will discuss all these things in detail when we will discuss the control hazard, then we will discuss this particular branch related instructions in detail. But for now, if we will generate this address, if the processor will generate one address for PC at this stage and another address for PC at this instruction, and during say at the let's suppose the processor is at 5th clock cycle, then which address will have to be considered by the pipelining to fetch the new opcode. This confusion will remain over there, because two parallel addresses will be generated, one by this, another by this. In unpiped line structure, it is okay, because only at one time only one stage is going to perform its operation, rest of the stages are not going to perform its operation. But in pipeline structure, if one address for the PC will be generated by this stage, and for any other instruction for the fetching of the new instruction in the first stage, this PC will generate this new PC address, then there will be a confusion and there will be mixing. So to avoid this confusion, address generation will be done by this particular stage only, and the rest of the detail we will discuss when we will discuss the data path required for the branch related instructions. Okay, each stage of the pipeline, as we can see that each stage of the pipeline structure is performing the different operation in the same clock cycle for the different instructions. So each pipeline stage will have to be separated from and connected to the following stage using pipeline register. So to store the data temporary, to store the data of each and every stage, to store the outcome of each and every stage either in the form of data or in the form of control signals, set of registers will be inserted in between the two stages, which was not there in case of unpiped line, because at one time only one stage is going to perform the operation. But here in the case of pipeline structure, each and every stage will have to perform its operation independently, and there may possible the outcome of the second stage may be directly used by the third stage as well. In some cases, we will discuss all these things in detail when we will discuss the data hazard. Then it will be more clear what is the need and why there is need to store the data of each and every stage within the register. For now, each and every pipeline stage will have to be separated from the next stage with the help of a set of register to store the data of that particular stage. Okay, so there will be a set of registers over here which will be used to store the data of this first stage, fetching stage, and this is called IF ID stage, and this is again a register set of registers in between the second stage, which is the decoding stage, and in between the execution stage. So that is why the name of this register is called ID EX. Similarly, execution and memory, this will be another set of registers which will be there in between third and fourth stage. Similarly, each and every stage will be separated with the set of register. So at the end of the each clock cycle, result of the one pipeline stage have to be stored in the pipeline register used by the next pipeline stage. So as we have already discussed that what is the need of this. So all these things are written over here. So these registers again cannot be accessed by the user. These registers are internally accessed by the processor only, and these are called the temporary register and will play the similar role as NPC new program counter, register A, B, which are the temporary register, ALU out, which is also a temporary register, load memory data register. All these registers are there in the data path. So similarly, these set of registers will not be accessed by the user, and processor is going to use for its internal use. Okay. So again, we have already discussed that these registers are used to carry the data and control from one pipeline stage to the another, and this result, whatsoever the result will be stored by this set of register, will remain there until it is no longer. Okay, so this is what is the role of the pipeline register. These are also called the latches, which are used to store the data and control from the one stage of the next stage. So now we will try to understand the instruction flow within the pipeline for a DLX processor. So we will take one example. Let's suppose LWR3 50R1. Let's suppose we want to load the data from the memory whose address is 50. So what will be the first stage will do? Hardware stage 1, which is nothing but fetching. It will do what? Will read the data from the external memory to fetch the opcode, and the address of that memory will be given by the program counter. So whatsoever the address of the program counter will provide the address from that particular memory location whose address is given by the PC, the opcode will be loaded to the IR. Opcode will be loaded to the instruction register, and that will be stored into the IFID register latches. Okay, so what will happen other than this? During this, whatsoever the contents of the PC over here will be incremented by 4 to assign the new program counter, and which will be the address of the next instruction which will be executed after the completion of this particular instruction. The next is for the second stage, read IFID register. The second stage will do what? It will read whatsoever the data is stored into the IFID register. It will be read by the second stage, and what it will do, it will receive a 32-bit long opcode from the fetching stage, and will decode it, and as per the need of the instruction, the source of the address of the source, address of the destination will be there. All these addresses of the operand will go to the temporary register. From bit number 6 to bit number 10 will go to the A. Whatsoever the address of the register which will be given over here for bit number 6 and to bit number 10 will go to the A. Similarly, for bit number 11 to 15, whatsoever the combination of these 5 bits will provide, accordingly the data or data of that particular register will move to a temporary register B. The immediate data from 16 to 31 will move to the immediate latch. Okay, so this will be what will happen during the decoding part, and all these things, register A, register B or immediate address, will be stored to the registers latches available for ID and execution unit. Okay, the third stage, which is the execution stage, as this instruction is the memory reference, so it will perform the operation that ALU will add the operand. So this ALU will add the operand to form the effective address, and that effective address, whatsoever the effective address from where data will have to be loaded from the memory. So in the fourth stage, hardware stage 4, in this particular stage, processor will have to access the memory as per the need of the instruction. Processor will have to load the data from the external memory, and whose effective address is already ready in the ALU out. So whatsoever the address will be assigned by the ALU register, data of that particular memory location whose address is there, whose physical address or effective address is there at the ALU, data of that memory location will be loaded to the LMD register. Okay, so it will be, the data will be accessed from the data memory and it will be stored there into the LMD register. So as the need of the instruction is to load the data from the external memory, so till this stage the data have been loaded from the external memory whose address was the part of the instruction and is already there in LMD. But still, as per the need of the instruction, data will have to be loaded to the R3 register. So it will have to write back to a register R3. Particular case, whatsoever the data will always be there in LMD, that will be loaded to the required register. That is, the address of that required register will be there from bit number 11 to bit number 15, which will be there in the register B. So after the completion or after the execution of the fifth stage, this particular instruction will completely be executed within the pipelining. So this will be the instruction flow of the within the pipelined DL structure. So this is all about this lecture. In this particular lecture, we have discussed what is the pipelining, what is the data path, what is the basic pipeline for DLX, what is the data path for this, and with the help of one example, we have discussed that how the data path will perform the operation. Thank you.